Hi everyone, good afternoon for the last session of this webinar. Here today, now we're trying to bring basically together what you have seen in the first two presentations. In the beginning of the webinar, you saw from Christian Huckel the importance of GLOF disaster management. And then in the talk just before the break from Perry, you saw some details about the RAMS software suite with the different modules of this software. And here in this presentation, I'm going to try to bring together and talk about some special characteristics of lake outburst floods and how we can address them when we try to model these outburst floods with the RAMS software. I will do this at the examples from the Andes to show a bit a different region, but similar processes that then you know probably. And what I will do, I'll first show you two examples of past GLOF events, and we talk about some special cases that are typical for lake outburst floods. And then in the second part, we try how we can address these characteristics and these peculiarities in modeling these processes with RAMS. In the background of this title, you see already the first case. This is Lake Salcantay, the Blue Lagoon. I try to, how can I have a pointer? Anyway, do you see my cursor probably? So this is the glacial lake that performed an outburst in 2020. And this was triggered by a larger rockfall or combined rock ice avalanche from this part of Salcantay Mountain, which is a 6,000 meter high peak. And these chains of processes is something very typical for lake outburst floods. This is a satellite image you see taken from the top. You see the lake, and you see here where you have the little one. This is the source zone close to the ridge here of this rockfall or combined rock ice avalanche. You see here how this site or this location here looked before the event. And then we had several 100,000 meters of mass that collapsed in February 2020 and was traveling down along these red arrows into an area close to the lake and actually also impacting this lake a little bit. You see this here. Now we have clouds in the source zone, but you still see the traces of this rockfall. This is a photo taken 1 or 2 days after the event. You also see the main impact of this flow was here going to the other side of the moraine, not directly into the lake. So this is here corresponding to these red arrows here and the area indicated with the 3. But of course, some part of the mass was also falling into this lake and causing a wave that is indicated by the blue arrows here. So this is a photo again taken after the event, looking now from behind the lake, from the area of these depositions. This photo is taken from about this location here, looking towards down the valley. And the arrows here indicate the direction of such an impact wave, how it was traveling through the lake and actually overtopping the dam. This is here again a photo you see indicated. There is a freeboard of this moraine dam of about 25 meters, but this wave was higher, the run-up was much higher, so quite a significant amount of water was actually overtopping this dam, causing some erosion. It was not damaging the dam, so there was not a breach that formed, but still large amounts of water were pushed out of this glacial lake and caused a major flood downstream. You actually can still see here on the very left of this photo in number 5, the upper reaches of the lake outburst flood, how it was traveling down and many kilometers downstream, more than 20 kilometers further downstream. This outburst flood was also causing significant damages to roads, bridges, and several houses. So this chains of processes is one very typical aspect, not only with avalanche impacts, but also with other lake outburst triggers. Very often, these lake outbursts are part of process chains. The other example I wanted to show you is an image you already saw earlier today in the presentation from Christian. This is a lake outburst from 2009 in Patagonia from Mount Tronador. You see the formation of the lake here on the right side, and then the outburst in 2009. You saw some of these images already, and what is very typical for this lake outburst event, but in principle for many or even almost all lake outburst floods, is that the flow type actually undergoes very often transformations of flow types. So a lake outburst flood as a term is a very broad term actually, and it consists of several different flow types. These can range from very granular debris flows up or down to hyper-concentrated floods, or even almost pure water floods, where we have only very small amounts of solid material entrained and water dominating the flood. And this is something you can also see here just from these several photos that have been taken in the first few kilometers downstream of the lake. So in some parts we have here deposits of really coarse debris flows, and then we have also traces of typical floodplains. So only fine material that is being deposited, and of course interaction with forest, woods, trees, etc. This is very typical. Lake outburst floods can travel large distances, and in these large distances they can undergo transformation from several flow types. And these are, I think, one of the most important challenges when we talk about modeling GLOF, and also modeling GLOF in particular with the RAMS software. So the first challenge, this modeling of interacting processes, of process chains, is actually again depicted here in this cartoon. So often we have an impact wave that is falling into a glacial lake. We have the formation and propagation of a wave in the reservoir, in the lake, and then we have run up and overtopping of the dam. Maybe you also have erosion of the dam if this is consisting of morainic material. And only then, after the water leaves the lake, we have basically the lake outburst flood. In this course, in the RAMS modeling course, we are basically focusing on this part here, on the flow propagation downstream, on the modeling of the lake outburst flood. However, one of the most important starting parameters or information we need to have a hydrograph at the dam. We need to know from some sources, information, modeling, whatever, we need to know how the hydrograph looks like at the dam to be able to use this as an input to be able to model the flow propagation downstream. Christian already mentioned these gap path guidelines for hazard assessment in mountain regions. This is very useful and basically will help to assess such hazards or potential processes, potential scenarios that can lead to lake outburst floods. In this part or this course, this webinar, we will not talk about the hazard assessment itself, but this is one source where you can certainly find relevant information. But I know also that many of you are actually in their daily business working with such assessment of glacial lake outburst floods and know how to assess lake hazard and also how to assess interacting processes and chains of interacting processes. My main point here is we need to have models that are able to simulate these processes, because for the RAMS modeling of the downstream, we need to have the outburst hydrograph at the dam. Second challenge of GLOF modeling is the flow type transformation as mentioned. And very often we have these different flow types in the dam. I also have here a graphic on the right side where you can see on the y-axis the volumetric sediment concentration, how high percentage of the flood consists of sediment, and on the x-axis how much of the sediment is a fine material or coarse material. And you can see on the left side photo as well a very typical trace of a larger lake outburst flood. So this here is the moraine. Behind this moraine we have the glacial lake. You see a huge breach that was formed during an outburst flood back in the 1940s of the last century. And you can see most of the coarse material is already deposited very close below the dam. And then you see this nice river here. In an outburst flood, this will be here mainly hyper-concentrated flood, so no coarse material being transported around, or very few blocks only. And then maybe later on, the terrain is again getting steeper and more process will be entrained, and the flow type will change again to a more granular debris flow. So the second point is also that erosion, and Perry also talked about this challenge of erosion that is also handled by the RAMS model. So it's also important to actually predict or to see in which parts of the flow the lake outburst flood can erode and entrain material and where deposition is actually predominant. In RAMS, in the debris flow model that you will be using, this is mainly handled by defining the friction parameters. There are these two friction parameters. And here I have a quite useful graphic that comes from a master thesis. And you see basically the two friction parameters on the y-axis here, the xi. So this is the turbulent friction, and the mu on the x-axis, the Coulomb friction. And you see here in gray circles, roughly, or ranges where for typical flow type, mass movement types, these friction parameter combinations can be set. So A here is representing debris flows. So debris flows are normally in these ranges of mu and xi friction combinations. The B is avalanches, C is rockfall, D is ice avalanches, and the E here is flood, so basically pure water flood. So this already gives us some indication, but then it's very important also to play around, and this is what you will then mainly do also in the on-site training later in June. Now, bringing this together in an example, I want to show you this case that has already been shown also earlier in the morning in Christian's presentation about this lake 513 in Peru. You see here this glacial lake. Below a very steep high mountain face under permafrost condition with steep hanging glaciers, etc. And this lake here again visible from a bit further away is located upstream of a city of about 25,000 inhabitants in the Cordillera Blanca in Peru. And in 2010, there was a lake outburst flood triggered by a rock ice avalanche. So you see the trigger was again such a rock ice avalanche, about 400,000 cubic meters of volume that detached here, traveled down the glacier and impacted the glacial lake. This is a photo of the dam of the lake taken the day after the event. You can still see the crushed ice of the avalanche floating on the water. And you see here, we know that these three tunnels, these holes here, the red circles, are tunnels of drainage, are 20 meters high. So you can already see here, the flood wave must have been 30 meters high or higher, and it was overtopping this bedrock dam. And then downstream, you can also see this flow type transformation. This is here the freshwater intake of the city, some few kilometers downstream. This is typically hyperconcentrated flood, so mainly water with some fine material in the flow. But also here, this is really the lake. This is a steep part, this is a flat part, and this is here the freshwater intake. You just saw the picture. And you can already see here in this part the different flow type transformations or the traces of these different flow types. So in one, close to the lake, we have basically pure water, huge amount of water, several 10,000 cubic meters per second discharge. Everything was washed away. Then in the two here, in the steep part, these are traces of a granular debris flow. You see here this bright color is coarse blocks that are being deposited. And then here in the flat part, we have this hyperconcentrated flow that you saw in the photo before. And in 3, where the river is getting steep again, you can see here is again erosion taking place. New material is being entrained and transported down to the city of Huaraz. This is here photos of where the river is joining the main river in the valley. And you can see, of course, bridges have been affected, several houses have been affected, and also agricultural land has been flooded, and large blocks have been deposited here. So these parcels are cannot be used for agriculture anymore because of the lake outburst flood. Okay, now how do we address this? And what the exercise we did here, this is mainly the work of our former colleague Demian Schneider, who worked a lot with RAMS to first reconstruct this flood and then also to make a hazard mapping and modeling of potential future events at this lake. And you can see again here this chain of processes of an ice avalanche, an overtopping wave, and then a debris flow that does several flow type transformation on the way downstream down to the main valley. And this is the modeling how we did it. And this is exactly corresponding and very much in line with what Perry just said before. When we model process chains, what we also followed here is we try to model each process on its own and then have a moment of thinking and reflecting and take the outputs of the modeling into the next step process actually. So what we did here, we did a nice rock avalanche modeling with RUMs. Back in time, this was another module, but it's not important in this case. Then we had a hydrodynamic model to basically simulate the lake formation, wave formation, wave propagation, and also the overtopping, the spillover at the dam. And this model gave us the hydrograph that we then used for the GLOF modeling of the downstream, which only starts actually at the dam of the lake. Here you can see the three scenarios that we modeled. We took three scenarios, small, middle to large. Small scenario was corresponding to the event of 2010 with an ice avalanche of almost 500,000 cubic meters. But we also modeled larger events of medium and large magnitude, going up to an avalanche volume of 3 million cubic meters combined of rock and ice material. And here you see the corresponding hydrographs at the dam. So the three colors are the three scenarios. Green here is the small scenario. The purple one is the medium scenario. And this greenish triangle here is the hydrograph of the large scenario. And this is the hydrograph at the dam. And what we did, you see this by these black simplified triangles. We tried to simplify these hydrographs and use these triangles as an input into the RAM's debris flow module to model the downstream propagation of this lake outburst flood. This is how this looks like. Just to explain this here, the red part here, this is basically the rock ice avalanche that we modeled. I'm not going to talk about this. Then we have the wave propagation with another hydrodynamic model. And starting here at the dam of Lake 513, we have the RAMS modeling of the lake outburst floods. And now considering these flow type transformations, we had here the, say, lucky situation, at least lucky for the modelers, that we have these traces or this evidence of the 2010 event. And we could see in which part of the flow, which flow type was actually dominant. And according to this information, we also defined the frictional parameters according to the observed flow types. So in the first place here, this is really at the dam, we have basically pure water flood with a very low mu value here. And then further down, we have this granular debris flow, and then a flood, a hyperconcentrated flow in this pampa with the freshwater intake. So these three sections here are what I've been showing as photos before 2 slides ago. And then further downstream, we have again a viscous debris flow with again different friction parameters. And then at the debris fan, at the place where it's also joining then the main river, we have a hyperconcentrated flow with again different flow type parameters. So what we did here, we actually prescribed the flow type and set different flow type parameters for the different sections of the flood. And by the way, you can also see here the hydrographs at different sections, which was also important to get the arrival times of the flood, which is very important information when it comes then to the planning of early warning systems. If you look at these friction parameters that are indicated in this graph, and I'm again showing here the slide or the figure I showed you before, you can see that we are here moving around in this circle, in this A circle of debris flows. So you can see, depending on the flow type, the Xi value is always the same, set as 500, but the mu, so the Coulomb friction, is moving from very low values, basically pure flood, very low friction, to higher values in parts of the flow where we have a more granular type debris flow, maybe here in this deep section below the dam. This is then the results for the three different scenarios, the reconstructed one, the medium scenario, and the future scenario, of course, a much larger flood here. And the result of this, what you have already seen in Christian's presentation, a hazard map, which can be used for risk mapping, spatial planning, etc. So that's why we actually applied all this RAMS modeling. So to sum this up, two main challenges for GLOF modeling with RAMS, but also in general, also with other software, is that we very often have to deal with chains of interacting processes. And the second challenge is this flow type transformation and also erosion that takes place along the course of the debris flow or the hyperconcentrated flow or whatever type the lake outburst flood might take. And we try to address this challenge first of the interacting processes by first a comprehensive hazard assessment, that we actually know what processes are involved and that we're then able to model all the processes and interactions before actually, because what we need and what's the aim of this hazard assessment and modeling is that we have a hydrograph at the dam that we can then use for RAMS modeling of the lake outburst flood. And for flow type transformation, we have an estimation of flow types that we can have maybe from past events or based on topography or of material. Is it debris material? Is it rock? Is it soil? Whatever. Then very important for this is also the erosion part, and RAMS is able to consider erosion to actually simulate how much sediment can be taken up by the flood and how it will be entrained and added to the flood volume, etc. And very important here, and this will also be an important part of your on-site workshop then, is to play around with different combinations of these friction parameters to see how sensitive the model results are on erosion, for instance, and how the erosion is considered, etc. So these will be the challenges and the tasks also you will deal with then once you will get hands-on training with RAMS. That's it. I hope I was more or less in time. Thank you for your attention and looking forward to your questions. Thank you.
Thank you very much, Holger, for the presentation. We have one question from Ulan from SAYAC. If I understand it correctly, it is about DEMs and if there are any quality requirements and limitations to the resolution. So maybe I would also like to extend the question to Perry from a technical perspective, if there is a upper threshold to the size of a DEM that can be imported in RAMS. But first, I would like to say that, of course, this is a trade-off. In principle, you would like to use the best DEM possible. But on the other hand, if the resolution is too high, also the computation time will be much longer. So especially for GLOFs, where the event can propagate for several decades of kilometers, you might actually want not 1 meter resolution DEM, even if this is available. And then, of course, for many cases, we don't have such high resolution digital elevation models. And then we have to get the best possible, which often it's in the range of 10 to 20 meters resolution, at least for open access, open source products.
One point to add on this question is also, so maybe just to add two things. First, what I showed you here, these results is based on a commercially obtained DEM from Digital Globe. So this had a resolution of 8 meters. So this was definitely perfect. And as you say also, Alessandro, regarding computational time, this was about the optimum. So higher resolution would mainly result in also higher computational times. But the other important point I want to make is resolution, of course, is important, but also quality of the DEM. Especially if we talk about open source, sometimes there are little artifacts in the digital elevation model, especially actually in the channel of the flow. And you can even guess from this picture you see here, sometimes it's almost a narrow gorge. And in this narrow gorge, if it's an optically or a DEM obtained from optical imagery, there can be obstacles or artifacts and little things, little obstacles, artificially obstacles in the flow channel. And this can have very strong impacts on the model results. So I would just, my point is not only look at the number of the resolution, but also have a detailed look at the quality of the digital elevation model. In my experience, this is sometimes the limiting factor is more the quality actually than the resolution, as long as you stay within these 10 to 20 meter of resolution.
Thank you, Holger. Probably also, especially with vegetation or when, yeah. So small scale details are necessary. In the chat, I see some more. So if the flow meets the erosion zones at the beginning of the breach, but then from forest zones, how will the modeling change? So if I understand the question correctly, from Nazir Zoda, what does happen when there is a vegetated area with trees? Is that correct? And in this case, I would forward the question to Perry if he's still listening. But I would say that in principle, in the continuum approach, you are not modeling single trees, as would happen for the rockfall, but you would change the friction parameters accordingly. Perry, do you want to add something? No, okay. Then there is another question for you, Holger. If it is possible to simulate GLOF as a result of intermoraine channel outburst, so ground flow, and what kind of input data are needed for this?
Yes, thanks for this question. So what we cannot do in RAMS is to model the evolution or the formation of intramoraic channels. But in our approach here, this would be part of, say, the hazard assessment, because we need from somewhere, but this could be done maybe with other numerical simulations, with other numerical models, to get a simulation of such channels. Because what we need for the RAMS modeling of the lake outburst flood is a hydrograph. And the formation of these intramoraic channels, they determine basically the shape of the hydrograph, so how long the outburst is taking place, what's the peak discharge, if this is a triangular shape normally or whatever. And this hydrograph we can then use as an input parameter to start the resulting downstream outburst flood to model this with RAMS. But within RAMS, we cannot simulate the formation of intramoraic channels, if this answers your question.
Yes, on this, I would like to add, in principle, a different model will be needed to model the discharge in the ice or in the moraine. As Holger showed before, they used IBER for the breach, and then a different geotechnical software could be used to calculate discharge from the moraine channels.
And in case no information is available, it can also, of course, also be a guess. I mean, you can by hand assume, or you can assume any hydrograph and include it into the RAMS modeling. Yes.
Yeah, we will talk a lot more about this during the workshop. This is, I would say, the input hydrograph and the erosion coefficients and parameters will be probably the main focus of the last days of the workshop. Then there was still a question on the friction parameters in vegetated area. It's not possible to answer generally. This depends on the type of forest that you have, what kind of trees, how dense they are, in which type of terrain they are found. And this is up to the modeler to define. So if you have a very dense forest, of course, this will have a higher impact on the simulation than if you just have a few trees on a large meadow, as you can imagine. And then we have another question from Yusuf. Reinbeckhoff. On what basis a breakthrough hydrograph is constructed? So how can we define an input hydrograph?
Yeah, so in the examples I showed, this was calculated with this hydrodynamic model. So this is an open source hydrodynamic model. You need lake bathymetry and you need the input mass movement in this case that you just see on the screen still. And this hydrodynamic model allows you to simulate the wave propagation, the overtopping, and it's actually the result of this hydrodynamic model is such a hydrograph, as you can see also on the right side here. The red line is the output of the hydrodynamic IBER model. And then we just took a simplified triangular shape approximation as an input for the RAMS modeling. But basically, as before, it's not, I mean, RAMS, you can also define this whatever input hydrograph you basically think is reasonable. I mean, you can, of course, have a numerical model that gives you this information, or you can have an estimate from a past event. So then you can basically manually define such a hydrograph. This is all possible. But the main point here is that for RAMS, using RAMS for downstream GLOF modeling does not provide you such a hydrograph as an output, but this is an input you need to define from whatever source, either from modeling, either from experience, or just from a scenario develop. I think that's the important part of the answer.
I completely agree. And maybe as an add-on, the main parameters are, of course, the volume of the lake that will discharge. And you can probably estimate these by doing bathymetry fieldwork to assess the volume and to imagine if all the lake will be drained or just a part of it. And then the second important thing is the time scale of the drainage. If you expect the lake to drain within minutes or hours, this will make a huge difference for the input hydrograph and the results of the flood later that then is modeled in RAMS.
You can see this basically here. So this is a wave that is just overtopping. So this is very short. You see this is about 12 seconds down, up to, in the large scenarios, maybe 30 seconds of duration, but a very high peak discharge. So this is really a lot of water, 180,000 cubic meters per second. So a huge wave in very short time. But of course, if you have breach formation, for instance, this is a process that can take a duration of several hours. Or if it's about channels in the moraine, it can even take up to days. And then the hydrograph will look completely different, of course. But this can be handled by RAMS for the simulation, but not, this is an input that needs to be defined, yes.